Alright, this is a short video on the properties of ionic bonding or ionic substances. This video will encompass three basic properties. One is the idea of ionic compounds forming a bulk crystal. This will result in numerous properties of ionic compounds. Then we'll be looking closely at melting points and then how an ionic compound dissolves. First things first, bulk crystal. I'm going to just take a quick moment and let's just describe how an ionic compound is formed. Let's say, for example, we have NaCl. Sodium starts out as sodium metal with one valence electron right there. Then we have chlorine, which has got 1, 2, 3, 4, 5, 6, 7 valence electrons. This is your typical Lewis structure. This guy here is going to be giving this guy an electron, and electrons being transferred, and that is, of course, is a property of ionic compounds. Electrons not being shared, they're being transferred. This guy therefore results in Na plus 1, and this guy results in Cl minus 1. The fact that it lost an electron forming a cation, this process is called oxidation. Something we'll see more in the next chapter. This guy's gained electron is called reduction. Now, at this point, we have a whole bunch of sodium atoms which have given electrons to chlorine atoms. And just because this guy gave this chloride an electron, making it negative, this guy therefore is positive, doesn't mean these two are exclusively attracted. Any cation, any positive charge will be attracted to any negative charge, and vice versa. Two positives will repel, two negatives will repel. But we have a whole clump of them, so we end up getting a little pile of cations forming, and given the opportunity, they will in fact form a somewhat of an orderly pattern, since the negatives and the positives repel each other. And I'll just draw a rough example of this. Do one more row. This is just on a two-dimensional plane, but you should be aware that this is taking place on a three-dimensional axis as well. This is what I commonly refer to as a bulk crystal, and vice versa. It goes up and down all directions. You could split this right down the middle, and it would be still the same sodium chloride on each side. So there is no way to know exactly how many cations are here or how many anions are here. So what happens is scientists will give this thing a name based on the ratio of cations and anions. This might be right here. There's one cation for every one anion. This is referred to as the empirical formula, and I'll just type that right here. This is the simplest ratio of atoms. Therefore, an ionic compound's formula will always be a simplest ratio. For example, NaCl is correct, but Na2Cl2 is not correct. That would be assuming or making some sort of inference that these four or any four have some special connection, and they don't. They're just a big pile of cations and anions. Bulk crystal is an important property of ionic compounds. Melting points of ionic solids. Now, the premise of that whole bulk crystal is that it's being held by cations and anions. What attracts cations and anions is simply going to be Coulomb's law, which is going to be the force is equal to some equalizing constant times the charge on the cation, the charge on the anion, divided by the distance squared. This governs pretty much all of chemistry. We'll start first about the charge difference. When you have a cation and you have an anion, now I'm going to still draw it. This is the nucleus here. I'm going to say this happens to have a few more extra electrons therefore making this one slightly negative, or my anion. This one's got a few less negative particles around the outside here, therefore making it slightly positive, making it our cation. And these two are going to attract between them. The strength of this attraction has to do with the quantity or the magnitude of the positive charge and the negative charge. That is this value and this value here. Obviously, the more charge you have of either or, the more they're going to attract. So at this point, we could make a little assumption here that increased charges yield increased forces. This is therefore going to give you, will therefore give stronger bonds. An example of this would be if we have a salt that is, let's say, NaCl versus, let's say, aluminum chloride. This guy is +1 -1 versus +3 -3. In this case, we have a larger positive charge here that would cause this cation to attract more readily to the anion and making a larger force. Larger forces yield stronger bonds, higher melting points. You should be able to build any anions for ionic compounds and arrange them in order of increasing melting points purely based on their differences in charges. This describes the top part of our formula. Now, the bottom part of our formula is dealing with the distance between them. And this is a little bit more, you have to think about it a little more abstract. But let's imagine a scenario where we have an atom, and I'm just going to draw a simple little atom here. And of course, this atom has electrons around the outside. The only reason why the electrons are staying there is because they are attracted to the nucleus. Now, the nucleus is radiating its, I would call, electric fields, and it is therefore attracting any negative that is in that field. So, if another atom happens to come along, I'll draw another atom right here, and it has, let's say, electrons here. If this electrons, and there are lots of them, but if this atom were to move into this electric field, then the electric fields of this atom, let's say atom A, and let's say atom B, if B moves into the field, it could theoretically rip the electron right off and keep it for itself, making it an anion. B would therefore be a cation. But if it doesn't have enough strength to simply take it, or it might just simply attract it and pull the whole atom over to its side and keep that electron near it, positive here, and we have them just kind of sticking to each other. I sometimes make the analogy of playing tug of war with a dog. You can pull a rope held inside a dog's mouth, rip it real hard, and the rope comes out. Or you can grab it and pull on it, and the dog keeps hold, and you can sometimes swing the entire dog all the way around. Either way, this is one way to attract. Now imagine another situation where we have an atom, and it is a much larger atom. So we've got a different situation here. We have a much larger atom. Okay, I'll just draw an atom here. And this guy is also going to be having more protons, so it's going to be having a larger attraction here towards the output. It's not maybe going to be able to reach quite as far. Therefore, the greater distance here is really causing a weak electrical attraction on the outside. So the electrons are actually are not held nearly as strong as the ones on the inside, or closer electrons. This goes exactly true for other atoms, electrons as well. We could have an atom again, atom A and atom B. Okay, atom B again has its same electrons. They're around the outside, and when he gets into this electric field, it's just so much farther away from the protons that it is also held much weaker, just like its own electrons are held weaker. So the attraction here between these two atoms is much less than these two. So when we say distance, we're talking about the atomic radius as opposed to the distance between the two or any other distance you might conceive. This example might be, let's say, sodium chloride. This would be the cation and an anion possibly. Whereas this might be, for example, barium chloride, where this guy is a much bigger atom, therefore has a harder time getting enough electric field to attract its anion with sufficient amounts. Therefore, let's make a little summary here that might say larger atomic radius yields weaker bonds and lower melting points. What you would want to be able to do is to, one, be able to separate out atoms relative to their charges first, and then if the charges are the same, then you'd want to do one involving radiuses. All right. So should first start with the charge difference, and if that happens to be the same, then you would then look at it and say, okay, well, maybe if there's a difference in the atomic radius, I'll use that as my secondary separator between melting point. The last thing we have here is dissolving ionic solids. Now, in any solution, there are forces holding a substance in solution, and there are forces that would maybe take a substance out of solution. Something's not just going to float for no reason. If I were to take a rock, for example, and I were to drop it into a beaker of water, it would obviously most certainly just drop to the bottom. For it to float would seem maybe a bit ludicrous. Well, it turns out that maybe it would float. If it does, there have to be two opposing forces, because there is one force that definitely makes it drop down, and that would be the fact that we are on Earth, and the fact that we're on Earth means that we have gravity. Anything that drops in here is going to be fighting off that of gravity. So gravity is one force. It's not usual that we would discuss gravity in chemistry, but in this case we are. So heavy particles, large, massive particles, like rocks, or in that case, atoms, bigger atoms, heavy atoms, metals, let's say like a silver compound. Silver is very heavy. Gold. We might have something like a barium. Heavy metals. Those are very difficult to dissolve into a solution. But what if something does dissolve? And you can make analogies like likes dissolve likes, but in reality it has to do with Coulomb's law. Once again, force equals the charge, cation. I said cation, but it could be any charged particle, and then of course we have the distance between the two. So if I drop a particle in here, and let's just say, for example, it could even be salt. I'm going to say draw a new picture here. I'm going to extend the bottom a tad just so I can do a little bit better picture. And let's say I have a beaker here with my salt at the bottom. So cation, anion, cation, and I'm just going to draw a very simplistic picture here. Our PowerPoint that we have for this chapter has a better animation of this, and I would encourage you that if you haven't seen that yet to review that. It's on the website as well. Drop into this thing some solvent. Let's just say this solvent happens to be water, H2O. Water looks like this. Turns out that oxygen is very electronegative, and we really haven't discussed a whole lot about that yet, but this is making it slightly negative and makes this area slightly positive. Now, as the water drops in here, it turns out that as we get a water molecule in here, that the same force that holds together the salt crystal, which is electrostatic attraction or Coulombic forces, can in fact separate the particles. So the negative will break off of here and simply float into solution around and hover around all the positives of the water, and all the positives will break off and float around the negatives. a better picture would be, I'm going to draw a picture right here, where we're going to get our cations floating or huddling around this negative, and then the negatives will float around here. And eventually, these water molecules get completely saturated with ions, and then it simply can't dissolve anymore. But in fact, this water molecule is creating an attractive force that would in fact balance or exceed that of gravity, and therefore would dissolve quite easily. In fact, it's so tightly bound that a filter would not be able to separate it, centrifuge would not be able to separate it. Only way entirely to get this off here would be to evaporate the water out, and the ions will be left behind. The last property that we have of dissolving, one last thing I'll mention about this is that if we were to drop salt into a solvent that doesn't have a charge of its own, we call this water molecule as being described as a polar solvent. If we were to use a solvent that was nonpolar, then this ionic salt really would have no reason to dissolve into the solution, and it would simply be content, or it would be forced to stay in the salt crystal. This water is playing a bit of a tug of war with these ions, and in that sense the salt crystal would win out if it was a nonpolar solvent. The last thing we have here, just to kind of describe this, is going to be actually I'll go back to this slide. One property of dissolving, and I mentioned this in the PowerPoint, is the fact that when we have these ions dissolving in solution, we get a unique property coming out. Cations, anions flowing around independently in solution, and the way we would write this out equation-wise would be, extend this page slightly, is like this. NaCl goes to Na plus Cl minus. Or we could have Na3PO4 goes to Na plus, and there would be 3 of them, plus PO4 minus 3. Total of 4 particles, total of 2 particles. Either way, the more particles you have dissolved in there, the easier it is to, let's say, conduct electricity across this thing. We could put a little electrode in there, electrons will shovel across here up to another electrode and out. Unique property called an electrolyte. That's it.